Okay, good afternoon. Today we are going to do again kinematics problems. But what is the difference from what we have done so far in kinematics is, so far in kinematics, we looked at the rigid bodies, which are not, which are only translating, is what we assumed. Why? Because we have not considered the physical geometry of the system. So when you do not consider physical geometry of the system of forces acting on a rigid body, of even though it's bigger rigid body, we assume that is going to form a concurrent system of forces. So only the translational study is what we have done in straight line motion, that's called rectilinear motion, and curvilinear motion in a plane that we have considered. Right, so we have now understood what is rectilinear motion and curvilinear motion, looking at physically the path of the motion. Also, we were very much familiar with the kinematic equations for a general case where acceleration is not constant. There are 6 equations. Out of that 6, 3 primary motion equation, 3 secondary motion equation, right? And we have solved some special problems of curvilinear motion. Those are from projectile motion problem. So you would be able to understand the path of projectile in projectile motion is parabolic when you neglect the air resistance. And there are interesting problems that can be in a projectile motion, which is again a simplified curvilinear motion because acceleration is not varying in it. So you have an acceleration which is constant acting on a projectile, which is only motion and gravity. And that was an advantage of solving projectile motion problems. And also we have looked at in the last class, when we have a system of bodies under motion, accelerated motion, more than n number of rigid bodies under motion. For example, if you have to look at the motion of many number of cars on the traffic in a highway. So what is happening? You have a fixed reference is what you have so far looking at every accelerated body. That motion is what is called an absolute motion. But if you have to look at again relate this absolute motion of 2 accelerated bodies, then you have been understood the importance of relative motion concept. So any particle absolute motion can be represented by another body which is accelerated, its absolute motion, and the motion of the body of our consideration, its relative motion with respect to the consider other body motion. So that's exactly what we were writing is RA plus RBA is what is RB. So if I have to get my absolute motion of RB, it is simply vector addition of absolute motion of RA plus absolute motion of B with respect to A. So that is what we were looking at, and we solved the problem of relative motion. And also we had some group of problem called dependent motion that we will see while we solve kinetics problem. This is what I was telling in the last class and concluded our lecture. And today we are going to look at again kinematics. So you know kinematics means it's a study of motion alone without considering cause of the motion. But what is that today we are going to do is we are going to account the physical geometry of the system. So when you account the physical geometry of the system, unbalanced forces in the system would cause not necessarily only translation, also rotation in a body. So you'll see a body is rotating. That comes under the category of rigid body kinematics. Or it is a system where you have number of connected bodies have got a motion related to other. Then you may have one component is rotating, other component is translating. Maybe one will undergo both simultaneous translation and rotation and so on. So the motion of an individual component become complex in nature the moment you bring in the physical geometry of the system. So in such a situation, how do we solve the problem? What are the fundamental concepts that we should remember as far as generating kinematic equation is concerned is what I am going to introduce and solve some problems today to understand kinematics of rigid bodies. So for that, let me share my screen. So hope you are able to see the screen. And here, this is what we have seen, projectile motion problem. I just quickly browse through this. And then we were ending our lecture looking at relative motion, wherein we have fixed reference as well as the moving reference. So you look at two references to define an absolute motion of B. So that's what we say RB equals RA plus RBA is what is mathematically you are defining relative motion. Such concept is very important for traffic flow control or for aircraft navigation or ship navigation and so on. So this is very important concept. So what we have done is this one problem we solved where we looking at two bodies under motion. One is with the uniform velocity, another one is with the uniformly accelerated motion, and we were able to solve this problem predicting its relative motion. So we did this in the last class, and today I'm going to introduce to you a new topic. So this is lecture number 38. I think today this date 23/10/2020 October. We're going to look at rigid body kinematics or kinematics of rigid bodies, either way you can call it. So the moment you say that, you will see that you will have rotation comes into picture. So what we have seen so far is translation alone. In case of particle kinematics. Particle kinematics. So we have just finished this topic and we are entering into rigid body kinematics, where you can see rotation or translation plus rotation, and that motion is what is called the general plane motion. So we are going to solve problems of this group. So the moment I have rotation, I can have my kinematic equation for rotation and the kinematic parameters or motion parameters for rotation. Analogous way, how do I define for my translation? So in case of translation, what we have defined? In case of translation, the motion parameters are position. Just instead of writing it, let me put position, velocity, and acceleration. And this all are going to be function of time. So we looked at this radial relationship gives me primary motion equation, and peripheral or circumferential relationship gives me secondary motion equation. So this is what we have seen. So you can have x as function of time, v as function of time, or a as function of time is what is primary motion equation, or you can also write v as function of x, a as function of x, or a as function of v. So these are the 6 equations that I have to define a complete motion geometry of a translating body without considering cause of the motion. So these are called kinematic equation. What are these called? Kinematic equation. Out of this, these 3 are called primary motion equation, and these 3 are called secondary motion equation. You know that. So now similarly for rotation, what are the motion parameters that I'm going to define is, in place of x position, here you have a position called theta, called an angular position of rotating body. Correct? So pulley is rotating. I have a point in its circumference. So if that point at t is equal to 0 is in a horizontal direction, it is on a horizontal line. As the pulley rotates, that point of observation can have its displacement in an angular position. That's what is called an angular position, right? So theta. And analogous to velocity, linear velocity, you will have a velocity called an angular velocity. And analogous to linear acceleration, you will have an angular acceleration. And you will have similarly, these all are going to be function of time. So I will have 6 motion equations for rotation as well. 3 primary motion equation where I can represent theta as theta function of time, or omega as omega function of time, or alpha as function of, sorry, this is function of time, function of time, function of time. And I can also represent omega as function of theta and alpha as function of theta and alpha as function of omega. So I will have analogous 6 equations which are for again kinematics of rotation, rigid body rotation. So the way we defined our velocity as dx by dt, we will define here our angular velocity as d theta by dt. And an acceleration we defined as dv by dt. And here angular acceleration we will define as d omega by dt. So this we could write this dv by dt as v dv by dx. We will also be able to write alpha as omega d omega by d theta. So these are the analogous parameter definitions, right? So we have defined for a specific cases, like here velocity is constant, we had only the first equation, x is function of time. Similarly, if omega happens to be constant, a shaft is rotating at constant speed. So constant power output of an engine is measured by a constant speed of the crankshaft, say. Then omega is constant. When omega is constant, out of 6 equations, I require only one equation, that is omega as function of theta as function of time only. So this is only one equation sufficient. Like you have uniform motion here, it is uniform circular motion or uniform rotation, you call that as. So what is that equation? It's going to be theta equals theta naught plus omega t. Like you had an equation here, v equals v naught plus you had x equals x of t, right? X equal x naught plus v of t. So x naught is 0, then it is x is equal to vt is the only equation which was uniform motion. And here when t is equal to 0, theta is 0, then this goes off. So theta is equal to omega t is the only equation, that is again uniform rotational motion. This is also uniform motion, but it is angular motion. So similarly, now when it is not constant, only alpha is constant, what will happen? If this alpha is constant, so your these relations disappears. So this disappears and this disappears, and only you have 3 relations. Theta is function of, so you have first equation, you have this equation and this equation and this equation. So only these are the 3 equations sufficient when alpha is constant, because alpha is constant, omega is function of t is the one equation, theta is function of t is another equation, second equation, and not this. Alpha is constant. So if this is constant, then you will have the third equation, omega is function of theta, this. So these 2 will not come into picture. So you have only 3 equations, and those 3 equations we would nicely write if we are able to compare with the 3 equations that we had here. So how do you write that? So first equation is what? Theta is function of time. So you will be able to write as theta as equal to theta naught plus omega naught t plus half alpha t square. Then second equation is omega is function of t. Omega is function of t. So this is first equation. Second equation, omega is function of t. So omega equals omega naught plus t. Like u is equal to, here you have written v equals v naught plus at. Here you have written x is equal to x naught plus v naught t plus half at square. So these are the two primary motion equation. These are the two primary motion equation in angular means rotation motion, rotational motion when angular acceleration is constant. So what is the third equation? Is the secondary motion equation. So omega is function of theta, so that will be omega squared is equal to omega naught squared plus 2 into alpha into omega minus omega, theta minus theta naught. So like you have written here, v squared is equal to v naught squared plus 2a into x minus x naught. That's all. So the same way you have these three equations. So like we derived this equation from integral approach using this definition, the parameters, and then we were able to draw motion curves. You can do all such activities for rotational motion as well. So here also you can do motion curves like theta t diagram, omega t diagram, alpha t diagram, primary motion curves. And then secondary motion curves means it is theta, omega theta diagram, alpha theta diagram, or alpha omega diagram. You can do that same thing here as well. So it is just an analogous way. But only thing that you have to remember is the parameter here, position given by unit meter, and here theta is given by unit degrees or in radians. That you have to be careful. And here velocity is given by meter per second. Here you will have, this is radians per second. So this is most of the time theta will be considered when it comes along with the trigonometric term. Otherwise we'll say that in radians, in SI units. So this angular displacement or angular position is to be given in radians. And here acceleration is given by meter per second squared. And here it is radians per second square. So that's what is that important that you should remember. So if you have understood this, I'm going to now extend our understanding looking at an important elements that are common in the machineries.